All right, well, welcome to another lovely day of differential equations. And today's plan is to continue talking about second order applications. And specifically, we're going to look at circuits and how second order differential equations can pop up in circuits. Um, Obviously, once we talk about where they come from and how, where they are, setting them up is going to be real straightforward. And then once they're set up, we know what to do to solve. So we're not really learning any new techniques. We're just seeing another place where we can apply it. So we'll start with that, and then we're going to move on to a technique that we can use to solve any differential equation, or at least attempt to solve any differential equation when you've got no other plan, no other idea, right? You look at the pattern and you go, I don't see anything. I don't recognize this form. What do I do? Uh, well, mathematicians being who we are, uh, we have a way of doing anything. Um, you're not going to like it probably, but it works always. But I will save that for later. And of course, before we get to what I want to talk about, let me open it up to you guys. Anything you want to look at from the homeworks? And just FYI, I literally just changed some due dates. You probably saw that there were a whole bunch that were coming up due. Um, I've adjusted some because we're slightly behind schedule and they were kind of piling up. If you look at them now, there's like, I don't know, 8 of them that are due June 2nd. Don't worry, they're not all going to be due June 2nd. I'll start spreading those out as well. But just FYI, if you've been looking at the homework sets and wondering what's going on with dates, I filled with them a little bit. But anyway, any homework we want to look at? Any questions on what we've been talking about? Nope. All right. Cool. Well, then we're going to go ahead and just dive right into, oh, Jesus. Got me right under the wire. Let's see, 6.1, number 11. Let me go ahead and write that down here. All right, so let's go find that guy and take a look at it. All right, let me switch my screen or share my screen so you guys can see it. All right, so number 11, which is just kind of right in the middle of this right here, it says a unit mass hangs in equilibrium from a spring with constant k equals 1/16. Starting at t equals 0, a force of 3 sine t is applied to the mass. Find its displacement for t greater than 0. Okay, so this is going to be a second order differential equation because we've got a mass on a spring. That f of t equals 3 sine t, just imagine that you got the mass hanging here, and then all of a sudden we just start applying a force that does this, right? So we're applying some external force. So really all that's going to do is make this so that it's a non-homogeneous differential equation. So that's what that's going to do. Let's think about what we need. We need m, k, and gamma, right? So if we start, it says a unit mass hangs in equilibrium. All right, so what's its mass? What does that mean if we say unit mass?
1, I'm guessing.
Yes, that's just mass 1. So in this, you notice how they didn't actually give us units here? Like there aren't any units. So this is 1 pound, kilogram, whatever. All right, it's 1 in our whatever system we've got. So there's our m. They also tell us our k, right? Because they literally say here spring constant k equals 1/16. So then what about gamma? Where does gamma come from? What tells us gamma in general?
The drag or air resistance.
Yeah, so it's the resistive force. So it's going to come from the drag and all that. And what kind of drag do we have here? What kind of resistance do we have? Well, I don't know about you, but I don't see any. right? And it doesn't actually say anything about drag. So I think it's safe for us to assume that the drag is actually going to equal 0. Okay, so this is going to be in a, there's no drag. We just do our thing. All right, so let's get this thing set up. Let's put these numbers and forcing function into the setup, and then let's see what we got. So I'm going to go ahead and switch to a whiteboard. All right, so in general, how do we do this? Like, what's this general setup for a spring problem? Because they all have the same form.
mx double prime plus gamma x prime
Good.
plus kx equals f of t.
Yeah. All right, so this is our, in general, what this is going to look like. So for our specific one, number 11, the mass was 1. We are assuming that there is no drag because they didn't tell us anything about drag, so we definitely can't do much about it anyway. The k was 1/16, and then our forcing function, I think I remember it to be 3 sine of t. All right, so here's our differential equation to solve. We'll worry about initial conditions in a minute, but let's actually just solve this first. So we'll start with the homogeneous. We'll get our fundamental set of solutions. So we get r squared plus 1/16 equals 0. So r is equal to plus or minus 1/4 I. All right, just move that over and take the square root. It is negative, so it does lead to the complex. So that means that in terms of our homogeneous solution, all right, I'll actually even write that YH for homogeneous. Complex, we need e to the lambda t. Well, there's a 0 there, so there's no e to the t. And so then we're going to get C1 times cosine of 1/4 t plus C2 sine of 1/4 t. All right, so always start with the solution of homogeneous. And now we're going to go find a particular solution. So what method do you want to use here? Please don't say variation of parameters.
Yeah,
I was thinking reduction of order.
I definitely like reduction of order because this is, oh, actually, no, I don't want to do reduction of order either. I want to do undetermined coefficients. This is a nice form, right? What kind of functions are going to give me sine when I differentiate?
A
Well,
cosine.
either cosine or sine. So I would suggest we use undetermined coefficients, but we could use reduction of order because we do have one of the fundamental set, right? And we also could do variation of parameters because we've got both of them. Remember, variation of parameters, that's the one where we make the Wronskian matrix. And then we multiply it by the matrix that holds 0 and then our f of t. So we can do that as well. But I think because this is a nice form, 3 sine t, let's just do this. So y p prime is going to be minus a sine plus b cosine. So then y double prime p is going to be minus a cosine minus b sine. So when I put that back into my differential equation, I get negative a cosine of t minus b sine of t plus 1/16 a cosine t plus 1/16 b sine of t. All right, so that first part was my y double prime, and then this is my, or x double prime, I should say. And then this is my 1/16 times x. And of course, we need that to equal 3. All right, well, if we just group by, or if we just combine sines and cosine stuff, we get minus 15/16 a cosine of t minus 15/16 b sine of t. So that makes A 0 because there are no cosines. And then for the B, we need negative 16/5. Okay, so there's our particular solution then is minus 16/5 sine of t. All right, so cool. We got our homogeneous and we got our particular, which means we just put those together. And we get y is equal to minus 16, no, not 15ths, 16/5 sine of t plus c1 cosine of 1/4 t plus c2 sine of 1/4 t. All right, so there's the general solution to this. But now we do want to take into account some initial conditions because we actually have them. So let me go back. We'll go and switch back to the homework question here. Now let's go read it and let's see if we can figure out the initial conditions. Okay, so unit mass hangs in equilibrium from spring. Starting at T0, a force is applied to the mass to find its displacement. So I guess the real question is at T equals 0, what's its initial position, right? What's its position at T equals 0 and what's its velocity? So let's start position. What's the position of it at 0?
0, right?
Yeah, because we're at equilibrium. Because we're at equilibrium, saying at equilibrium, that means that it's at 0. All right, what about what's its velocity at 0?
Well, it's also 0, I guess.
Yeah, that's correct. That's exactly right, Victor. It's also 0 because it was just hanging there in equilibrium, minding its own business. Nothing was going on until the force started driving it, right? So initially, both its position and its velocity were equal to 0. So let's go back to the whiteboard and let's take care of that. So we do know that x of 0 equals 0 and x prime of 0 equals 0. So we'll go and we'll plug those things back into here. When you plug 0 in, all of the sines go to 0. The cosine goes to 1. So we end up with 0 equals nothing plus C1 plus nothing. Okay, so that tells us that C1 is equal to 0. All right, so that means that that part's not even there. Nice. So then to get the other, let's look at what the derivative gives us. So the derivative of this thing, let's do it over here. And I apologize, I'm calling it y. It was actually x, you know, habits. But I get minus 16/5 cosine of t plus 1/4 C2 sine, or sorry, cosine of 1/4 t. All right, so when we plug in 0 for that guy, we have 0 equals minus 16/15 and then plus 1/4 because the cosines are both equal to 1, or 1/4 C2. So that makes C2, if I calculated this correctly in my head, 64/5. All right, so we'll just replace that with the 64/5, and there is the equation that is going to give us the position of the mass at any time. So like I was saying, that we're going to see with the circuits, is like once you figure out how to put things in, once you get yourself to this spot here where you've got your differential equation, then we just turn on cruise control, right? It's like driving an automatic car, you know, one of those self-drive cars. You just sit in there and let it do its thing. Well, what is the thing here? Well, start with finding a solution to the homogeneous, then find a solution to the particular, then put them together, then use your initial conditions, and right, it's the same thing every time. And really where the variation comes in is in the solving of the homogeneous, because sometimes you might have to use a different method there, and solving of the particular. There's definitely different methods that we use for that one, depending upon what it looks like. All right, so how was that for number 11 from 6-1? Is that good, Jesus? All right, so any other homework questions? Or are we good to move on? Okay, sounds like we're good to move on. So let's actually look at another place. Oh yeah, you're welcome, Jesus. Let's look at another place where we get second order differential equations. On this one specifically, let's look at circuits. So I think, well, I know that at least all of you but one have seen this. But I'll give you kind of the real quick lowdown on circuits, the real quick physics on it, and then we'll see how these second orders pop up. So let me go ahead and come back to the whiteboard, and let's just start with a real quick kind of review of circuits. Now, for this circuit, I'm actually going to allow every possible element in it. Okay, so here's going to be our circuit, and this will be our, say we've got a switch that we can then have our EMF.
What's the second one again? Is that a...
Okay, yeah, I'll go over that in just a second. So let's just say that this is our EMF right here. Okay, so the EMF, usually you actually see that with a circle, but this is our power source. So it can be a battery, or it could be the wall socket, right, or whatever, but there's something that's actually giving us power. This jagged guy over here is a resistor. And even if we have more than one resistor, we can always combine them into one mathematically, depending upon if they're in series or parallel. I'm not going to get into that, because whenever we set these up, we're going to assume we have just one plain old resistor. Okay, so that's a resistor. This is an inductor, the one that's a little like curly guy here. That's an inductor. Real quick, so resistors, those are things that basically are using the energy. Like when your light bulb turns on, the electricity is going through the light bulb. It's like it's a resistor, and it's taking some of that energy and converting it to light. But so the resistor is like the functional part. Inductors do exactly what they do, or what they sound like. They induce currents. Great examples of where we use inductors are like if you've got, say, a rechargeable electric toothbrush. So you think about your electric toothbrush, you know, it's self-contained, you brush your teeth, but then when you need to charge it, you just set it onto the little stand, and magically it charges up. right? Or maybe you've got a phone charger that does the same kind of thing. You just take your phone and you slap it down on it. That makes use of induction. It actually produces a current in something else, so that's an inductor. And then this guy with the sort of like separate parallel lines, this is our capacitor. How about I write a C? It's a capacitor, not an capacitor. Capacitor. And a capacitor is something that actually stores up charge. It builds up charge, and then once that charge kind of gets full to a point, it will arc over and actually start the flow again on the circuit. A great example there is like your intermittent windshield wipers. I don't know if you've ever thought about that, but intermittent windshield wipers have a capacitor. It's charging, it's charging, it's charging, it gets full, and then your blades go. Charging, 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 gets full, blades go, right? So that's what a capacitor does. And then we'll have an EMF. The EMF usually actually what you'll see for a symbol for an EMF is again like two parallel lines, but one's bigger than the other. But we'll assume that there's some power source. Okay, so this is a switch, just FYI. So if you ever see a symbol like that, that's a switch in your circuit. So like right now, this circuit is open, nothing's going on. So we would expect no current. There would be no flow of electricity through this circuit because there's nowhere for it to go. Okay, but now if I close the switch, now we know a current is going to go, right? That there's going to be movement of charge that's being driven by the power source. When I write EMF, that stands for electromotive force. And that's what it is, right? It's a force that causes electricity to move, electromotive force. So battery or the outlet, the plug into the wall or what have you. Okay, so we close that switch. So let's say that switch gets closed. And now we're going to start getting a current. And let's talk about what happens with the current as it goes across each of these things. So what we really want to look at is the voltage drop over each of these elements. Think about voltage. I always go to gravity. I think about this as like water flowing. So the electricity is water, and then the voltage is kind of like the hillside. As you go across each one of these things, you're going to drop a bit, and your hillside, you're going to drop on your voltage. So I'm curious if anybody remembers. Let's start with the resistor. Does anyone remember how much voltage you lose over a resistor?
V equals IR, right?
All right, awesome. Good memory. So here, V is equal to IR. So I, this is the current, and R is the resistance. And it's in ohms are the units of resistance. Current is in amps, and voltage is in volts. Okay, so we have volts, amps, and ohms. Again, in case you don't remember, you'll see the capital of omega. That'll be your symbol for ohms. But yeah, that's exactly right, Jacob. Good memory. V is equal to I times R. So we get current times resistance. All right, so how about inductors? Do you guys remember the voltage drop over inductors? Oh, it got awfully quiet.
I don't remember talking about inductors, but maybe I'm just,
No,
off my
I'm
game.
with you, Bradley. I don't remember inductors at all.
Okay, well, maybe Kathy didn't talk about inductors.
You They produce a magnetic field inside, right?
Yeah. So basically, yeah, it's creating a magnetic field, which then allows an electric field in the other thing, right?
Yeah, I remember about that, but not
Um,
voltage.
okay, so and that I can totally see that sometimes. I know when I've taught E&M, if I'm running low on time, I skip inductors because they're not as important as resistors and capacitors. So let me just give you then the voltage drop over an inductor. Okay, so again, it's going to be in volts, and it's L times di dt. The L, this is your inductance, and the unit of that is henries, as in the person's name. All right, so inductance is always a certain number of henries. And just like resistance is a property of the resistor, the inductance is a property of the inductor. But the voltage drop, it's equal to L times di dt, so the rate of change in the current with time. So you actually need to have a change in current for there to be any voltage drop over an inductor. If your current is constant, this would equal 0. And then there's actually no voltage drop over an inductor, so then it's not doing anything. So there always has to be a change in current flow. If you think about it, that should kind of make sense, because if you start changing the current, then you're changing the electric field. So there's a change in electric field, which then can lead to current in the other object. Actually, a really good example in the lab is if you take just a coil of wire and then you drop like a magnet through that coil, it can make a light bulb light up, because now that magnetic field is inducing a current. Anyway, so that's for an inductor. It's just L times di dt. So you can just kind of take my word for it if you've not seen it before, but that's what we get for our voltage drop there. And then how about for the capacitor? I know you guys must have talked about those. Does anybody remember how much voltage drop there is on a capacitor?
It depends, right?
Well, okay, it depends on what kind of capacitor. I don't know if that's what you meant by it depends.
It's Q equals CV or something, right?
Okay.
Where Q is the charge.
That was awesome. Yeah, so if you go back and you look at that, you see that the voltage, it actually is going to equal Q over C. So I think that when Jacob said it, I think you said Q equals V times C, which is the same
Q
thing.
equals, yeah.
But I want to write it as
Structure.
V equals, since we're just looking for voltage drop. But again, good memory. And here, so C, this is the capacitance, which again is the property of the capacitor. And then Q, this is actually the charge of the capacitor. So as the capacitor builds up charge, the voltage drop across it increases. Okay, so again, your capacitance is going to be what it is. It's a property of the capacitor. And then you throw the switch, it starts charging up, right? Because current is bringing charge to it. So it's changing its voltage, but there it is. Excuse me. All right, so yay. So now if we think about it, that drop over voltage of those three has to actually be the same voltage as our EMF. So if we think of this EMF as having some, well, I don't know, f of t as our function here, we can put this all together and it creates a differential equation. You can definitely see it here, where we get over the resistor, we get I times R. Over the inductor, we get L times I prime. Oh, hey, look, differential equation. Plus 1 over C times Q is going to equal F of T. All right, so there you go. But something should bother you just a little bit about this, for those of you who remember your physics. And that is, there are actually two things that are changing. The I is changing. So clearly the I prime is as well. But also the charge is changing. That depends on T as well. So last physics question for you. Do you remember how charge and current are related?
Isn't it Q equals like I times T? I might know that sounds wrong.
It's not. You're close. You're definitely close.
Isn't it current charge per area?
So current is the change in the charge. It's the movement of the charge. So it turns out that this guy I is actually Q prime. It's dq dt. So when we measure current, we're actually looking at what is our change in charge with respect to time. All right, so if we recognize that, then notice that this I is a Q prime, and the I double prime is a Q double prime. So we put this all together, and what we see, let me actually write it the way that you would think about saying it. You have L times Q double prime plus R times Q prime plus 1 over C times Q equals F of T. And all these guys, L, R, and C, those are all constants. Those are going to be characteristics from this circuit. Like I said, if you have multiple capacitors, we know, how, again, in physics, we learned mathematically how to put them all together as if they are one capacitor. And that's what you would do. And then you would put that C in here. Oh, and it just dawned on me, I never did tell you. Capacitance, for those of you who don't remember, those are in farads and charges in coulombs. Anyway, just so you've got all your units. But here it is. There's our second order linear, right? It's linear even, second order linear differential equation. And it even has constant coefficients, which makes it even better. Because when we want to solve it, at least the homogeneous part, we know exactly what to do. Okay, so there it is. That's how this plays out. So let me show you with an example of what the setup's going to look like, just so that you can see how to get it set up. And then in terms of the solving it, well, it's as easy as solving any of these other ones. So let me go ahead and just clear some space over here. We'll keep that formula up, but let's get rid of some of this because we don't need it anymore. that should be plenty for us here. But let's say this is our deal. All right. So for example, suppose that we've got a circuit has a capacitor of capacitance. Let's go with 1 times 10 to the minus 5 farads. A resistor of 300 ohms. And an inductor of 0.2 henries. All right, and let's maybe say that the capacitor is initially charged at a Q of 10 to the minus 6 coulombs. And there is no current. All right, so what we're going to do then is we're going to, the switch is closed, and what we're going to do is we're going to find a function for I of t. Okay, so we're going to see if we can figure out what the current is at any given time. So this is the typical kind of problem you're going to see with these. Obviously, there might be some variation, but for the most part, that's what they look like. So let's start by just sifting through this information and finding the important stuff. So we got a capacitor of capacitance, 1 times 10 to the 5th. Okay, so C is going to equal 1 times 10 to the 5th, or to the minus 5, sorry. The resistance, well, that's right here. It's 300 ohms. The induction is 0.2 Henry, so L is 0.2. So we can check. We got all those. This bit right here where it says the capacitor is initially charged at 10 to the minus 6 coulombs and there is no current, that gives us our initial conditions. This tells us Q of 0 is 10 to the minus 6, because that's the charge that's in the circuit at the start. And there is no current. Well, remember, current is Q prime. So Q prime of 0 is 0. So all of that gave us our initial condition. Right, so it says switch is closed, and then find the function for the current. Okay, cool. But what about f of t? What's the f of t here?
I'm thinking it's 0 since the switch is closed.
Okay, it's 0, but not because the switch is closed, but because there is no power source. We're not attached to a battery. We're not plugged into the wall or anything. This is we've got our inductor, resistor, and capacitor all set up, and there's just a little bit of a charge on that capacitor. All right, well, you close the switch, things are going to happen because of the fact that there's charge on that capacitor, but there isn't any electromotive force. We don't have a battery. We don't have the wall socket. We don't have anything like that. So it turns out f of t is 0. So as a differential equation, this looks like 0.2 q double prime plus 300q prime plus, well, 1 over that is 10 to the 5th times q equals 0. And so here's the differential equation that we need to solve. All right, well, there it is. Not too bad, right? So let's go ahead and solve it. I'm going to multiply everything by 5 just to make that be 1 q prime or q double prime. So we get q double prime plus, what's that? 1500 q prime plus 500,000 q equals 0.
Shouldn't the multiplier on Q be 10 to the minus 5?
Hold on, no, because it's 1 over c.
Got it.
So if it's 1 over 10 to the minus 5, it's 10 to the plus 5. But good catch on that, just in case. But I'm fairly certain that this is what we want. All right, so if we go to the now solve the homogeneous, because that's all we have to solve. These are constant coefficients. So I just have to take care of this polynomial. And luckily, this one's nice in factors. So we get minus 1,000 and minus 500. So we're going to get Q is equal to C1 times e to the minus 1,000 t plus C2 times e to the minus 500 t. All right, so now let's use our initial conditions to find C1 and C2. So if we go with the Q of 0 equals 10 to the minus 6, so we got 10 to the minus 6 is equal to C1 plus C2, because both of those, when we put in 0, go to 1. And then for the derivative, we're going to get 0 equals minus 1,000 C1 minus 500 C2. Those minus 500 minus 1,000 come from taking the derivatives. And then the e parts again go to 1. All right, well, there's our system. And we can actually go ahead and solve this for C1 and C2. If I multiply this by 1,000, so that the C1s cancel, I'm going to get 500 C2 is equal to 10 to the minus 3. So C2 is going to be 10 to the minus 3 divided by 500, which is 0.2 times 10 to the minus 5. So I think that's 2 times 10 to the minus 4. He says with serious doubt in his voice. I think. That's C2. So then we can get C1 in a similar way. It's going to be 10 to the minus 6 minus 2 times 10 to the minus 4, which is negative 1.99 times 10 to the minus 4, I think. Again, we're going to go with it. If those are wrong, they're wrong, right? You get the idea. This is what I get for just doing it in my head. But so we put those back up into here. And what we've got now is our formula for charge. Charge is going to be minus 1.99 times 10 to the minus 4th e to the minus 1,000 t. That's 1,000 t plus 2 times 10 to the minus 4 e to the minus 500t. So those are tiny, right? These are small numbers, but that's what our charge is at any given time. So you'll see that it's like, all right, yay, we just put in our numbers and we solved it like we solved every one of these dozens and hundreds that we've done so far. And yeah, it's exactly the same. But I want you to notice that we haven't actually answered the question. What do we still have to do to actually answer the question?
Initial condition things or find.
Actually, we used the initial conditions already. That got us these. But Ralph just put in the chat box, we need to find I of t. So we definitely do need to derive it. This is Q. Remember, I, that's equal to Q prime. So if we want to find our current, we have to differentiate this. So multiply by minus 1000 gives us 1.99 times 10 to the minus 1. And then multiplying by minus 500 on this one gives us a minus 1 times 10 to the minus 1, e to the minus 500t. And this actually is going to give us our current at any time. And this actually tells me that I botched something with my C's. Because when I plug in 0, I don't get 0. So check that on your own, but you kind of see the point here. But check out what's going to happen with this. Look at this function. What happens to this function as time goes on? Both of these drop off to 0. So what we should expect is eventually that current drops off to 0. Does that make sense?
Yeah, because everything is discharging and there's no flow or F of t.
Yeah, there's no power source, right? So there will be some initial current because of stored charge. But once we let it go, it's going to drop off to 0. A really good example of this is like inside of TVs and monitors and computers and all that, there are capacitors. And have you ever noticed how like I'm trying, like you turn off the TV, but it still like glows a little bit? I don't know that that happens so much with newer TVs, but if you go to some of the older TVs, you can see that there's still like a little bit of a glow. Or you turn off your computer and the power light is still glowing a bit, even though it's off, and then it fades away to nothingness. If you've ever seen that, that's exactly this. There's still capacitance, there's still charge on the inside that's being stored. It eventually trickles away from like this exact same setup. So anyway, really the moral of the story here is, here's another completely different physical situation that leads to a second order differential equation, and there are tons. There are absolutely tons of them throughout physics. So when you run into these problems, just realize all you got to do is be able to pick out the L, R, and C, and maybe be able to figure out what the initial conditions say, right, or how to interpret those from the wording. But once you plug it in, it's business like usual. All right, so any questions on this example other than my weird C1 and C2s that don't actually work? No, we're feeling all right with that? All right. So let me just pop back up here now. All right. So I could show you examples of second orders all day. I could show you that for the rest of this quarter, but it's not going to serve you well because as you've seen, it's just a matter of getting it set up. And once it's set up, you do it. So we should probably talk about other techniques, other things that we can do when the techniques that we have don't really work so well. Because think about it, like for first orders, we know exactly what to do. If they're linear, no problem. If they're separable, we're mostly good. It's if we get into some other weird situations, then it can get kind of brutal and we may not have a technique. But for most of the first order, we're good. For second order, that's not the case. We know really well what to do if it's linear and we've got constant coefficients. In that situation, we know exactly what to do. If it's not in that form and we don't know a fundamental set, it gets more challenging. We can fake it a little bit if we can find one of them, right? Use reduction of order, that kind of thing. If we have both of them, but it's not a nice form, that's good too, because then we can use variation parameters. But all of that is predicated on knowing at least one of the functions in your fundamental set. And those are not always obvious. So obviously the next question is, well, what do you do if you've got no clue? You have no idea what the fundamental set are. You have no idea where to even begin on trying to make a guess of a function because, it clearly isn't going to be sine or cosine or, e. So what do you do? Well, you're going to do what mathematicians always do when they don't know what a function is. And this is something I don't know if you've really run into it yet, because most of the time up to this point, we know something about the functions and we can kind of, wing it a bit. But the ultimate tool of, I don't know what the function is, I need to figure it out, is to use power series. Yeah, go ahead, get out of the way. Groan. Give me the power series. All right. So power series, remember what power series are. They are describing functions as infinite polynomials. And we've seen that we can do that almost always. I mean, there are some issues like if you're trying to divide by 0 or things like that. But in general, we have ways of finding power series. Remember Taylor's formula? Crickets, right? That's the one where you differentiate, divide by the n factorial, and do all that good stuff, right? So we have, Victor just gave me the frowny face on the chat. Yeah, so we've got Taylor's theory, formula, Taylor's theorem. So we can always do that, and that's what we're going to do when we're presented with well, I got no better option here. I'm not really sure. We're going to guess that our function is a power series. And we're going to find out, well, what does that power series look like? What are the coefficients forced to be from the differential equation? So I'm going to show you, we're just going to start with an example. So let me pull up my whiteboard again. I'll get rid of all of this stuff because Lord knows we don't need it anymore. But suppose I'm going to give you actually a nice, simple differential equation. Okay, so this is one that is super easy, no big deal. So let's say we've got this one. We're going to go with y double prime plus xy prime plus y equals 0. And I'll even give you some initial conditions. I'll tell you that y of 0 is 0, and y prime of 0 is equal to 1. All right, so this is what I want to solve. Now, we have probably no idea what kind of form this is going to take on. I think you could maybe say, could it be a polynomial? Because when you take polynomials and you differentiate and all that, like maybe, right? Maybe it's a polynomial, but maybe it's not. Or maybe it's a polynomial times something else, or maybe it's, you know, who the hell knows. All right, so when we run into something like this, if you have no better idea, what you're going to do is you're going to make a guess, and you're going to say, I think Y is a power series. In fact, I know I can make a power series for Y. I just don't know what it might be. And the generic power series, to kind of remind you, looks like this. So it's the sum from 0 to infinity of a sub n. Those are the coefficients on our polynomial. And then we have x minus x naught to the n. I think when we did this in calculus, we called this C. Okay, so that's our center. So that's where we're centering our power series, because we can put it wherever we want. Okay, now when we're doing one of these where we have initial conditions, we're going to use the initial conditions to determine what x naught we're going to use. So in this specific example, since we're doing y of 0 equals 0 and y prime of 0 equals 0, we're going to choose x naught to equal 0. So just to kind of remind you, because I know it's been a while, it was like at least a year ago when we did power series in third quarter calculus. The center, we know that our power series converges at the center, meaning it's defined there, it's part of the domain. And we know that we're going to be good in some interval that surrounds the center. So when we have an initial condition, we want to pick that to be the center. We want to be at that spot when we move away. All right, so that's why we're going to use the initial conditions to do that. So for this specific one, then we're going to go with y equals the sum from 0 to infinity of a sub n times x to the n. And our goal here is to find the a sub n's. Let's start building this polynomial of infinite degree. All right, so if this is our y, we definitely need to get a y prime and a y double prime. All right, now I don't know if you remember this about power series, but this is one of the reasons why we like power series, is that when you differentiate a power series, you literally just have to differentiate this piece that's an exponential piece, because a sub n is a constant, it's just a number, n is a power, so we have x to the n, so this becomes n times a sub n times x to the minus 1. But there was one little thing that we had to pay attention to, and that was that the start of our power series gets bumped up by 1 when we differentiate it. So there's our derivative. So then the second derivative, this is going to be the sum from 2 to infinity, because we got to bump it up again. But then when I differentiate this, the n and a sub n are all constants. So I just bring that n minus 1 out front. So I get n times n minus 1 times a sub n times x to the n minus 2. And this is actually one of the reasons why we really like power series, is that their derivatives are crazy easy. Like, you don't even really have to think about them. Okay, so now what we're going to do, just like every time we've made a guess, Well, what are we going to do? Every time we made a guess and we've done this, we did the y prime, y double prime. What do we do at this point?
Plug in into the function.
Yep, we just plug them into the original differential equation and go, all right, well, what does that force these things to be? So we're going to take all of this and we're going to put it back into the original differential equation. So I'll run that up here now. So we're going to get y double prime. So that's the sum from 2 to infinity n times n minus 1 a sub n x to the n minus 2 plus x times the sum from n equal 1 to infinity of n times a sub n x to the n minus 1. And then plus y. So n equals 0 to infinity a sub n x to the n, and we know that that needs to equal 0. So what we're going to do is we're going to find all of the things that are like powers of x, group them together, and then make sure that their coefficients match what's over here. In this case, they're all going to have to be 0. So think about what this one looks like. We'll write out the first few terms. So when n is equal to 2, I get 2 times 1. So 2, a sub 2 times x to the 0. The next piece, when n is 3, 3 times 2 is 6, a sub 3, x to the first. The next one, now when n is 4, 4 times 3 is 12, a sub 4, x squared plus dot, dot, dot. Okay, so there's the first one. Second one, let's do the same thing, but let's remember that we got an x out front here. So we're going to get 1 times a sub 1 times, well, this is x to the 0, but then times another x is x. Plug in 2. I'm going to get 2 a sub 2. All right, 2 minus 1 is 1, so that's x times x is x squared. We'll do one more. You get 3a3x cubed, and I'll put plus dot, dot, dot. So there's that guy. And then this one is super easy because it's just our generic power series. All right, so let's just start grouping them by powers of x. So if we go for constants first, if you look at the constant terms, the x to the zeros, we get 2a2 plus a naught. We go to the x's. We have 6a cubed plus a1 plus another a1. So 2a1. All of that is times x. Okay, let's go to the x squareds. I have 12 a to the 4th. I have 2a2 plus another a2. So plus 3a2 x squared. And so on and so forth. All right, now this actually is going to tell me a little bit about the a's. Because if you look at this first piece, for example, where we've got 2a2 plus a naught, I know that that is going to have to equal 0. Because that's what my differential equation is equal to, right? So the constant piece has to equal 0. Similarly, I know 6a3 plus 2a1 is going to have to equal 0. And also 12a4 plus 3a2 is going to have to equal 0, and right, a whole bunch more. If I wanted to, I could have found more of them. All right, so basically this leads to a system of equations. All right, well, let's just start kind of breaking this apart and figuring out what those different A's are.
I have a quick question for you.
Yeah, go for it, Bradley.
So before we get to the system that we have, what's the justification for stopping, because we should be going to infinity, right?
Correct.
What's the justification for stopping at, say, n equals 3?
I
4?
stopped there because I didn't want to go any further and write out any more. I mean, honestly,
Okay.
because in reality, yeah, there are an infinite number of them, and we would have to continue this process, right? After that 12a to the fourth plus 3a squared, or 12a sub 4, there's going to be the next one, which is going to be 20a sub 5 plus 5a sub 3, I think. That's going to have to equal 0. And then there's the next one, and the next one, and the next one, and the next one. So they do literally go on forever. I just stopped here because I can't go forever, and I figured this was enough for where I want to be right now. In the real world, like if you're having to do this for some, some research project or something, you're going to want to go as far as you can, take as many terms as you need for it to be a good enough approximation for you. And you can use things like, I don't know if you remember back when we were doing power series and stuff, like there was a way to determine what your remainder was if you were to cut it off. It's always based on the next piece. And so what you can do is if you go, all right, I need to be within a certain amount, you can use that formula to figure out how far do I have to go until my remainder, my difference, is less than that. And that would tell you how many of these A's you're going to need.
Okay.
Right? Like
okay.
the way I've got mine set up is the last A I'm going to get is A sub 4. But if I wanted, all the way out to A sub 37, well, I'm going to keep going down on the terms until I get through A sub 37.
I guess I should have waited for the punchline at the end.
No, that's all good. But it's the same kind of thing that always happens with power series where we go, yeah, this is great. This is great. And we can use it as an approximation, but we always have to be careful about where do we turn it off. Because if it's an infinite polynomial and it never actually ends, as soon as we end it somewhere, we're introducing, error, right? We're no longer exact. All right, so here's what we're going to do. We need to just start with some values. And here's the thing. You'll notice that A0 is kind of a free choice. I can let that be whatever I want because there's nothing here that says what A0 should be. But once I pick A0, then I definitely know what A2 is. There's going to be a relationship here, right? Like if I just rewrite this, A0 is equal to minus 2 A2. So A2 is going to be minus 1/2 A0. So if you told me A0 is 20, okay, well then I know what A2 is. A2 is going to be minus 10. Or if you said A0 is 16, all right, A2 is going to be minus 8, and so on and so forth. But here's what I'm going to do. I'm going to let A0 just be A0. All right, and we'll just start making a list of what these things are going to equal. So we got A0, A1, A2, let's put in an A3 and an A4 since I've gone at least that far. All right, so if I know A0, then A2 is going to be minus 1/2 A0. But check this out. If I know A2 and I run over to this piece, I can get A4, right? 12A4, not A9. I really wish my pen knew how I like to draw my 4s. All right, so 12A4 is equal to minus 3A2. So A4 is going to be minus 1/4 A2. Well, if A2 is minus 1/2 A naught, that tells me that 1/4 is going to be 1/8 A naught. All right, so at least so far, this is what we know. Now, A1 is another free choice. A1 can be anything I want, because when I come here, notice A1 is not dependent on A0. So A1, I'm just going to call A1. But once I know A1, I know what A3 is going to be. It's going to be minus 1/3 A1. And you know what? We're going to do another one just because. Let's get an A5. If we move to the next term and you go back through the power series and plug it in, you're going to get a 20 A sub 5. That was me saying 5 and writing 4. That one I can't blame on the pen. 20 A sub 5. And then in terms of the x cubes over here, I'm going to have my 3a cubed plus another a cubed is 4a cubed, or 4a sub 3. So those are going to be the coefficients on my cubes. So a5 is going to be minus 1/5 a3. Well, a3 was minus 1/3 a1, which makes this 1/15 a1. So we'll go ahead and put that down here as well. All right. But I think Bradley's point was well taken. Obviously, we only know now through A5. If we want more, we'd have to go further. But let's take this then and put it into our power series just so you can see what our function's starting to look like. So I've got the first few terms. Don't have all of them, not even by a long shot, but I definitely have the first few of them. And it's starting to look like this. So y equals a naught plus a1x minus 1/2 a naught x squared minus 1/3 a1 x cubed plus 1/8 a naught x to the 4th this should be a plus 1/15 plus 1/15 a1 x to the 5th plus ... So we actually have the first 6 terms. At this point, we've built the first 6 terms of this function. But notice how there are a bunch that have a naught and there are a bunch that have a1. I'm actually going to split this into 2. So let's take the a naught and factor it out from all the pieces with a naught. So we're going to get 1 minus 1/2 x squared plus 1/8 x to the 4th plus ... And then the ones with the a1s, we've got x minus 1/3 x cubed plus 1/15 x to the 5th plus ... All right, so do we know exactly what this function is? No. But at least we know kind of what it's looking like, and we've got the first few terms of it, and of course we can find more terms and more terms and more terms and more terms, but it's starting to look like this. All right, so we just slugged through a bunch of algebra basically to get us to this point, but here's what I hope you notice. Remember how I said a naught and a1, those were free choices? That's our C1 and our C2. They're just renamed. These 2 things that are in parentheses, those are our fundamental set. So if I were to translate this back to the language that we know, or we write this as C1 times Y1 plus C2 times Y2, A naught is C1. The stuff in the parentheses here is Y1. A1 is C2. All this stuff in parentheses is Y2. So notice that even though we just started with a generic, hey, it's a power series, we still ended up getting exactly the same form. It's just these Y1 and the Y2, we don't know what they are. Well, at least just looking at them right here right now. Sometimes we will. Sometimes we'll be able to look at them and go, oh, that's the power series for e to the x, or that's the power series for sine of x, or whatever it happens to be. But one thing for sure we're going to want to do is see if we can spot patterns here. See if we can spot what the relationship is, so that we know what the next term is, so that we can actually write it in series form. Because then if we write it in series form, we have the solution. We have all infinite number of terms in our polynomial. All right, well, so remember we had initial conditions, right? If you come back and look at this, we had y of 0, 0, y prime of 0 equals 1. That's actually going to allow us to find a naught and a1. And believe it or not, it's way easier than you probably think when it comes to these. Because here's the deal. Remember how we chose to center it at 0? Look at what happens when you plug in 0. What happens in these things when you plug in 0?
The first one you get 1,
Yeah.
and then the second one you get 0.
Yeah. Everything that's x to a power is going to be 0. So if you always center it at the spot, the x minus x naught, whatever it happens to be, when you plug in your initial condition, those are all going to go to 0. So this is like crazy fast. Y of 0 is going to equal a naught times 1 plus a1 times 0. So a naught. We knew y of 0 equals 0, so a naught equals 0. And then when we go to the derivative, this is also pretty fast, because when we differentiate, you get 1. And then this one's going to be minus x squared plus 1/3 x to the 4th, ... But all those guys with x's, again, go away. Just equals a1. So in this case, a1 is equal to 1. So there are your initial condition results. We get a naught equals 0 and a1 equals 1. Which means we're actually good now with our solution. Let me go ahead and write it here. So y then is going to equal x minus 1/3 x cubed plus 1/15 x to the 5th plus ... It's only this second guy. So check it out. We found the solution to this differential equation. It's an infinite polynomial, power series, but we found its solution. All right, so I'm just going to go back in time just a minute ago. Well, a minute ago, now probably like half hour ago, when I said, you're not going to like this. You're not going to like this method. Am I right? You're not liking this?
Yes, you are correct.
Yeah, it's brutal. There's a ton of algebra. There's a lot of stuff we have to worry about. And we haven't even actually really finished talking about well, does the solution actually exist? Where does it exist? Because remember, when we have power series, we have to worry about things like, oh, I don't know, where it converges, where it diverges, and all that. So we just kind of made the assumption of, well, yeah, we can use a power series, and that's true. But the question is, how long is that power series valid? So we still got to talk about that. We should probably talk about, is there a faster way than drawing all these things out. And, you know, can we get to this relationship that we wrote out here, the A0 through A5? Can we get to that faster? Is there a better way of doing it so that we don't have to slug it out? Right. So there's still a lot to be said about these. But hopefully you can at least see why this method will always work. We'll always be able to find, well, as many terms as we want in this polynomial. So we can carry it out as far as we're ever going to need to in an applied setting. But it's a way of getting to an answer, even if we have no other recourse. All right. Well, here's something else that I want to show you that is kind of nice. You notice how this A naught equals 0 and A1 equals 1? Those were exactly the initial condition values. That's always going to be the case. So let's just start making this a little bit better by letting you know that if we use this power series stuff, A0 is always going to be y of 0, and A1, oh, let me not write 0. Let me write x sub 0, because that's kind of how we standardize that if we're centered somewhere else. But if our initial conditions are at x0, as long as you center it at x minus x naught, okay, so we're doing this guy, then always your initial conditions are going to be A0 and A1. So that should make everybody happy here.
Yeah, that's pretty convenient.
Yeah, it means that you don't actually have to do anything when it comes to these initial conditions. And hopefully you see exactly why, right? Like think about what this looks like if we were to write it out. You get A sub 0 plus A sub 1 times x minus x naught plus A sub 2 times x minus x naught squared plus, I'm just going to do one more. That should be more than enough for us to see what's going on. So if you plug in x naught, gone, 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 gone. All that stuff is gone, and all you're left with is A naught. And when you differentiate, okay, A naught goes away. You can get A1, because this is the linear piece. Then you get 2A2 times x minus x naught plus 3A3 times x minus x naught squared plus dot, dot, dot. And again, gone, 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 gone. The only thing left is your A1. So that's really good news. Really good news. Because then we don't even have to go with the, well, we don't know what A naught is. Yeah, you do. And if you feel more comfortable plugging that in, plug that in. So like when we were at this point right here, you just go, oh, okay, A naught is 0. Oh, look, that forces A2 to equal 0, which then, oh, when A2 is 0, that forces A4 to equal 0, and boom, boom, boom. And then the same thing here, you go, oh, A1 is equal to 1. So then A3 is minus 1/3. Okay, then we take our minus 1/3, right? So if you're one of those people that kind of has to have numbers to feel good about doing this, you've got them now. You've got them from your initial condition and you can plug them in.
I have a question for you.
Yeah, go, Bradley.
With the example we just did, I'm noticing that it's increasing power oddly.
Yep.
Is that because we started with a degree 1 polynomial attached to our y prime, or is it just how it happened?
This one just kind of happened that way.
Got it.
Just kind of happened that way. What you're going to find out is that when you do this, both of the y1 and the y2 can have any kind of x's. Like, yeah, maybe one's only even powers, maybe one's only odd powers, or I don't know, maybe it goes x to the 4th, x to the 7th, x to the 10th, right? Like, who knows? It could even have all the powers of x's, and that's going to be entirely determined by the original differential equation. And there probably are patterns, but I'll just be honest with you, I've not done enough of these to have spotted patterns. Like, oh yeah, if we always have an x times our y prime, we get whatever form. They may exist, but I haven't filed those away in my brain yet. But to me, it's just, well, you just follow what it says, see what the power series does. And there's a bit of a faster way to create these relationships. And looking at the clock, I'm going to have to show that to you next time. But we're going to be able to speed this process up a little bit. It's going to require us to do some things that you may not really like to do because they involve the power series. Like, do you guys remember changing your starting count, your starting point in sums? You change the order or the index. We're gonna have to do that. We're gonna look at actually combining sums by adding them and stuff like that. But if we do just some algebra on the sums themselves, it can make it so that it's much faster to find this relationship between all the different A's. And I can go a little bit quicker. But we'll save that for next time, because like I said, we don't have enough time really to do that justice. All right, so think about where we are. We just took a differential equation that was actually pretty nice, but it was different enough that we didn't know what to do with it. So we made a total guess, right? We guessed this form over here. And then guessing that form led us to, at least the first few terms of the actual solution. So we'll refine this. We'll speed it up. We'll refine it. We'll talk about when you actually can do it, how good it is, like over what interval, you know. So there's still a lot to talk about this, but at least now we've got a chance for anything, right? And you can see why when Bradley first asked that, you know, the beginning of class, when he's like, well, does this work only for second order? And no, it works for absolutely anything. Because we don't, I mean, it could be a 20th order and we would still do the same thing. You just have to get your 20th derivative of your power series, but that's not that bad. I mean, we know how to differentiate power series. So this is actually a really robust method. And if you're given some other function, like remember this one, we had x times y prime. If it had been e to the x times y prime, okay, we'll find the power series for e to the x, multiply that by the other power series. That's just polynomial multiplication. We can do that, right? So it's nice. It's really systematic, which means it's also really good for technology. In fact, quite a bit of what technology does when it solves things for you, when it does your calculus and whatnot, it does power series ideas. And yes, Victor, you're right. Sometimes that y we get will look like the Taylor series for specific functions. Like, I mean, just think about this one, the fact that we found one of them had all the evens and one had all odd powers. I don't know if you remember this, but like sine, its powers only odd powers. And it's and cosine's power series had all the even powers. So yeah, sometimes you'll go, oh, hey, that's a sine of x, or oh, that one, that looks like e to the x. So yeah, sometimes we're going to be able to actually know, right? Like absolutely know what the function is because we run into a power series that we've seen before. But I don't want you to get your hopes up because that's very rare. It's very rare that that's what we run into. Because usually if those are our solutions, we would have found them, you know, other ways. And the vast majority of functions out there in the world are horrible, nasty, shitty functions, right? Ones that we can't even describe. We do you a disservice by making you think everything is e to the x's and sine of x's and polynomials, because in the real world, they're not. They're just the ones that are really easy to differentiate and integrate and stuff like that. Okay, well, I think at this point, I'm going to go ahead and pause our recording, and wish you guys all a wonderful couple of days, and I will see you when I see you.